Okay, good. All right. Okay, so let's keep going. All right, so that's the warning of exponents. All right. So now we had exponents that were positive integers. What about exponents that are negative? Okay, well, for any non-zero real number a, okay, and positive integer n, a to the negative n is 1 over a to the n. A to the minus n is 1 over a to the n. In other words, when you negate the exponent, you do 1 over. And also here we're assuming a is not 0. Hopefully you can see why, right? Because if a were 0, then a to the n could be 0. Well, would be 0 actually. And you never divide by 0. You know, you can't have anything over 0. That doesn't make sense. And in fact, for any non-zero a to the 0 is 1. I'm actually going to show you why this is true later on. It's really not terrible once you have these rules of exponents. And these are just some quick examples I did. 2 to the negative 2 is 1 over 2 squared, which is 1 over 4, right? Negative exponent, 1 over. 3 to the negative 5 is 1 over 3 to the 5th, right? Negative exponent, 1 over. And this is just 1 over 243. This I actually calculated in my calculator. I can't do this in my head, so just letting you know. Yes?
Just to clarify, what you're just doing with the examples is you're flipping them. Like it's before you, so it's 2 to the negative second power over 1, and then you flip it to make that 2 negative 2 positive, correct? That's all you're doing?
Right, exactly. You're flipping it. Yeah. That's a good way of saying it. I really like that. That's good. Awesome. Okay. Right, you're flipping it. When the exponent's negative, you flip it. Awesome. Okay. Okay. Awesome question. Any other questions? Okay. Now, we said a was not 0. Let me just clarify what happens when a is 0. Well, 0 to the n is 0 if n is a positive integer. I mean, it's really not that, I mean, it's really just because you have n copies of 0, you're multiplying them together, and you know, 0 times anything is just 0. So 0 to the n, where n is any positive integer, is just 0. 0 to the negative n, that's not defined if n is positive. You know, you can't have 1 over 0. You can never divide by 0. And in fact, we have 0 to the 0. That's not defined. I know it's tempting to say this is 1, but it's nothing. It's not defined. 0 to the 0. Okay. All right, so that's a little bit about exponents. What about products? Well, exponents, you know, they do, let's see what happens when we do products, in other words. So I did put an example here just to illustrate what happens. But for any real number, right, let's say you're doing a cubed times a squared. Well, we know that multiplication is associative, meaning you can use parentheses, you can group them any way you want, you know, use parentheses. That's what I'm doing here, from here to here, associativity. Okay, but again, since it's associative, we really don't need these parentheses, so we can throw them away, and we have this. But how many copies, what is this equal to? Well, there are 1, 2, 3, 4, 5 copies of a. So this is really just a to the 5th. And we know 5 is just 3 plus 2. So when the dust settles, this product is the same as this. Now, I know that's not a proof, but hopefully from there, that'll help you see this rule, that if a is any real number, m and n are integers, then a to the m times a to the n is a to the m plus n. When you multiply like bases, you add the exponents. That's really what I'm trying to show. And that's really what I did here, right? Like bases, what do you do to the exponents? Well, in the end, we just added them. And that's what I'm doing here. Okay, well, let's see another example or two. Here, 5 to the 4th times 5 squared, right? Well, that's just 5 to the 4 plus 2, which is 5 to the 6. Here we have 8 to the 5 times 8 to the 7, which is 8 to the 5 plus 7, and that's 8 to the 12. Okay. Now I know these exponents are positive integers. Notice here I said m and n are integers. Technically, these could be negative. And the convention that the book is using is this. When we have an equation like this, okay, we're always making the assumptions that both sides exist. So if m and n, in other words, are both happen to be negative integers, then we're implicitly assuming a is not 0. I mean, if we did not make this convention, we would have a lot more writing to do, a lot more cases. If a is not 0 and m and n are negative, then we would have this equation as well. It's just really for convenience, that's all. So if m and n are negative, then, or if m and n are negative, for instance, we're also assuming a is not 0. We also assume that. I hope that makes sense. That's what the book is, that's the convention the book is using. I thought it would be good to explain that, so. All right. Well, that's for products. Okay, what about quotients? Well, here we need a to be non-zero because we're dividing. Okay, well, if you just, so for instance, if we have a to the 7 divided by a cubed, right? We have a times itself 7 times on top. A cubed is a times itself 3 times. There it is. Okay, but what's going to happen here? Well, there's going to be some cancellation, right? This is going to cancel. This is going to cancel. This is going to cancel. So after that cancellation, what do we have? We have a times a times, one second, what's that laser? There it is. We have a times a times a times a. So we have a times itself 4 times, a to the 4th, which is the same thing as a to the 7 minus 3. Okay, well, what am I getting at here? Well, I'm trying to illustrate this property. I mean, it's not a proof, but if a is a non-zero real number and m and n are integers, when you divide like bases, subtract the exponents. So we already saw multiply like bases, add the exponents. When you divide like bases, subtract the exponents. And that's just what I'm illustrating here. If you have 5 to the 6 over 5 squared, you end up getting 5 to the 6 minus 2, which is 5 to the 4th. Are there any questions about this? Again, I know I'm going through this kind of quickly, but again, I like to treat this stuff as review. Okay. So here I said I can prove why a to the 0 is 1, a is not 0, and that's what I'm showing you here. It's really not terribly hard. It's just based on properties that we saw already. If we assume a is not 0, okay, well then a divided by itself is 1. keep in mind, we need a to not be 0 because that's what I wrote down here, 0 over 0. That's not defined. It's nothing. It's nonsense in math, at least at this level. Okay, so we have this. We also know that a to the first is a, right? That was that was part of the first definition of exponents that we saw. Okay, well, using this in here, we have this, using our exponent rules. But we know if you divide like bases, subtract the exponents, and we get a to the 0. So we have 1, when the dust settles, is a to the 0. Same thing as saying a to the 0 is 1. I thought it was cool to throw in that proof. So, why something is true. Okay. Let me just pause this.